to Francis turbine also. So this question may come in the Francis turbine also. So what you do is, don't take a chance in this module as well as in the third module. In the third module, regarding the steam turbine, you prepare for everything. Anyhow, it is easy, graphical method. And in the hydraulic turbine, here also you prepare everything. See, if you prepare properly in this, the module 2 will be very, very easy for you. So I am stressing one in other way. If you prepare this module very well, the module 2 will be so simple that within 4 classes I can complete the module 2. Okay. So I am telling, so prepare well for this. Means don't skip the topics in this. In the last class, we're done with what do you mean by hydraulic machines? That there are 2 types of machines, hydraulic machines. One is turbine and pump. What do you mean by hydraulic turbines? Then we went for 3 types of hydraulic turbines. Classification of hydraulic turbines. It is based on the action of water, impulse and reaction. Example for impulse is Pelton. Example for the reaction is Francis and Kaplan, that you already know. Based on the direction of flow, based on the head of the water, based on specific speed of the turbine, based on water handling capacity. And this is a general figure of the, either you can say as impulse turbine, or generally assume, if we assume this as a turbine, if the water is coming, then you can tell it as a hydraulic. The exact figure for the impulse turbine is this. So this is what it is required in the examination to draw. If you ask you to draw the work with a neat figure, explain the working of a Pelton turbine, you have to draw this figure. Okay, you have to draw this along with the explanation. What is the explanation you should give? This one. The Pelton turbine is so and so, high speed, the water flow along with the inner curve of the bucket. All these explanations should give. Along with that, the main parts of the Pelton will also should be mentioned: nozzle, casing, runner buckets, and braking jet. So here you can include the braking jet in the figure only. Here it is not shown. You can draw the braking jet which is opposite to this direction, usually at the top. And the braking jet diameter will be very small compared to this outlet. Okay, this is only used to rotate the blades. Here the braking jet, if I use, draw the small nozzle and draw the figure in such a way that the water is hitting the bucket in the opposite direction with a small quantity, that you can draw the braking jet. And this video also is shown how the hydraulic turbines, how the Pelton wheel turbine is done, how it is placed, how the buckets are, why it is shaped like that. All those things I explained with the videos. Then, the last class I done with the dam, right? What do you mean by the dam? How it is going to work? All those things is covered. So today I will go for the reaction turbine. Today I'll go for the reaction turbine. In that, only the parts of the what is the input for the reaction turbine? Usually the input for the turbine, for the reaction from the reaction turbine is the pressure energy, partially pressure energy and partially there will be a kinetic energy. So the input energy available for the reaction turbine will be partially pressure energy and partially kinetic energy. But what is the input energy available for impulse turbine? Anyone can tell? What is the input energy available for impulse turbine?
Kinetic energy.
Hello? Only kinetic energy. It will be completely kinetic energy only. None other than the kinetic energy. But here it will be having both pressure energy and kinetic energy. As it proceeds from guide blades to the runner, both the energies will be utilized to rotate the turbine. So in this, you know what you mean by I think probably I not covered. I'll go through this. So Francis turbine is categorized. Oh, so this is covered. Now Francis turbine is done. Video of the Francis turbine is also done. So to start with, what I'll do, I'll show some more videos of the Francis turbine. Some more videos of the Francis turbine I'll show. Then I'll go for the Pelton wheel turbine, which is the last turbine in this module. Where the theory I'll explain. From the next class onwards, the velocity triangle related to Pelton, Francis, and Kaplan, I will explain. Is that okay? Hello? Anyone?
Yes, sir.
I have a question for you.
Okay.
What do you
So
mean
this
by
first I'll explain the working of this Francis turbine, then I'll go for Kaplan.
what we're looking at now is a Francis runner. see that the water comes in from the
Can you all see the video as well as listen the audio?
Yes, sir.
Okay. See how it is going to, how the water is allowed to go for the runner, how the runner blades will be, and what is the name of the runner blade. Here the name of the runner blade will be called as vanes, not as buckets. Okay. I'll play the video. You just have a look of this. 3 videos I'll play continuously, one after the other. Have a look of that. If you're having any doubt, ask. Okay. So in this briefly, I'll explain. This is a pipe. Okay. And if I connect these two, it will become like a spiral casing. And this is a shaft where the power is taken out. And this is called as a runner. See the shape of the runner, or it is also called as vanes. And this is called as guide blades. He will rotate and he'll show you. This is the guide blades where I can restrict the water flow to the runner with the help of this guide blades. Means if I close this guide blades completely, the water will not flow. Or I can smoothly allow the water to flow through this runner blades. That is the advantage of guide blades in this. But in Pelton wheel, there will be nozzle. From the nozzle, water will be directly heated to the buckets. So there is a damage. Damage may occur more in the Pelton wheel, but here it is not occurring. Damage will be very, very less in this because whatever the damage it is occurring, it is only occurring for the buckets. Sorry, guide blades, not for the vanes. We'll see.
It's delivered to the runner radially. The Francis type runner is actually a mixed flow turbine. The water is allowed to enter radially because it comes in from the sides, is drawn into the center, and then drops out of the bottom. So compared to an axial flow turbine, there's quite a lot happening. If this was an axial flow turbine, it would just flow in from the top, go straight through the runner, and drop out the bottom. Not so here. We're using radial entry, where we are flowing to the center of the runner, and then we are dropping out of the bottom in an axial manner. So that's why we call it mixed flow. Radial entry and axial discharge.
So the Francis turbine will be having radial entry, axial discharge. So it is called as mixed flow turbine. Okay. It is called as a mixed flow turbine. Why it is mixed flow? Because the entry is radial. Because this is a shaft. Center line for the shaft. With respect to the shaft, if you want to talk, the water will enter from guide blades perpendicularly, that is radially to the shaft, and then leaves the turbine axially. So what is the name of this tube? Can anyone tell? This blue color inner tube, where the water is going out from the runner. This tube is called as a draft tube. Okay? Draft tube, where the function of the draft tube is only to make the water to flow to the tail race. Means instead of leaving this with as atmospherically, so what they will do, they will put a airtight casing, and in that airtight casing, the pipe will be fitted. That pipe is called as a draft tube, and it will be having a conical shape. The water will be falled, means water will be allowed to flow through the draft tube, and it will discharge to the tail race.
Notice that we have quite a unique shape. The scroll case itself, sometimes called a spiral case, gets narrower as we loop back around to where the water enters the scroll case. The reason it does this is because we want to distribute the water to all areas of the runner in an even manner. And we can see the diameter of the water inlet here is very large. The diameter of the water inlet on this side gets gradually narrower as it comes around. See that if we zoom out. See gradually narrower, but this ensures that all of the water is delivered evenly to.
So this is the actual plant of Francis turbine.
Huge influx of water that just flows into the runner on one side. That would cause an imbalance, potentially vibration, which may even damage the runner. Not only that, but the runner is going to operate inefficiently. We use a wicket gate to feed the water into the runner. This is our wicket gate here. See that they're sort of plates that are mounted between the water suction side and the runner itself. The wicket gate is controlled hydraulically. See, we've got 2 hydraulic cylinders here. If one of the hydraulic cylinders, imagine for a moment this one where my mouse is now, if that was fully extended, then usually the other one on the lower side of the screen where my mouse is will retract. When they do this, they're actually going to turn this entire assembly here, and that is going to rotate the position of all of the wicket gate paddles. So all of these pieces here are going to rotate anywhere between 0 to 90 degrees. If the wicket gate is fully open, then the water is allowed simply just to flow through and go directly to the runner. If the wicket gate is fully closed, then none of the water is going to be allowed to flow through and get to the runner. We can use the wicket gate in an emergency to shut off the water flow, although it's more generally used for flow control. The wicket gate also allows us to angle the water as it enters the runner, and this increases the runner's overall efficiency. The upper side of the Francis runner is known as the crown, and that's where the runner vanes connect to the top of the runner. The lower side of the Francis runner is known as the band, and that's where the vanes connect to on the lower side. So let's discuss exactly what's happening here. Water is flowing in from the right and is gradually being distributed to the Francis runner as it passes through the wicket gate. As it flows into the runner, we're going to get a pressure differential created across the blades. Remember, this is a reaction type turbine, so the entire area is flooded, and this is a pressure turbine. I'm going to flow into the runner now. You can see I'm now in the middle of the runner. If I was water, I would now drop out the middle of the runner, and I would enter the draft tube. So that is the path of the water. It's relatively simple. Radial entry, axial discharge.
Remember this, radial entry, axial discharge for Francis turbine.
Turbines, we're taking the potential energy of the water and we are converting it into mechanical energy. Francis turbines are used for a wide range of applications.
See, this is this graph, if you remember, it will be easy for explaining either for Pelton, Francis or Kaplan. I will tell you how it is. See.
Because they're suitable for many different heads and many different pressures. This mixed flow turbine runner can pump water as well as act as a turbine. So it is essentially a hydraulic pump and a hydraulic turbine. Pump storage plants use Francis type runners. Now that we've looked at Kaplan turbines and Francis turbines, let's go and have a look at the final type of turbine, which is an impulse type turbine known as a Kaplan turbine. If you like this video and would like to see more engineering related tutorials with links or share it on social media, it really does help us out.
So I'll play the videos. So first, so that listen to that every video, so that you'll be having some clear idea about what is the meaning of Francis turbine. If you're having any doubt, We'll discuss.
Hello, welcome to the postgraduate program in Artificial Intelligence and
Yeah, this is done, no?
These restrictions make these two-kind turbines less common.
More of that. See how the water level is increased and how it is discharged. You observe this video. This is called tail race or channel, where the water from the turbine will go out like this, and this water will be utilized for the agriculture purpose, and it will leave agriculture purpose. Usually they will use this. See what the plant they are installing is, now they are installing the Kaplan turbine. Okay, installation is okay, but once it is installed, the working principle where the water comes, where it is discharging, it is same for Kaplan as well as Francis. In the Kaplan turbine, there will be 4 to 6 blades, but in Francis, there will be 12 to 16 blades. See, this is the generator where the electricity is generated. They are inspecting, they are installing that. Windings.
With
Just a minute. And they'll do the analysis part first before installation, before running the turbine. They'll do the analysis as you're doing in ANSYS. No, similarly, there is an CFD tool where you can do the analysis for fluid flow. These are all for the electrical students, will be helpful. How the shaft is produced. Measuring the diameter, inner diameter. Usually this portion will be for electrical students. Okay. One more small video, one more short, and the last video I'll show you. Whether this I have shown, whether this video is done. Hello.
No, sir.
Just a minute. See the shape of the casing. Okay, it's called a spiral casing or also called a scroll casing. Spiral or scroll casing. This yellow color portion indicates the guide blades where I can rotate this yellow color blades, angle everything I can do so that the water allow of the water to the rotor will be smooth. Class. Yeah, hello. Have you gone through the videos of all the plans? How the dams will be constructed, how the building of turbines will take in place, how they are installing, how it is going to place an actual plant, how the power is generated. I hope with this you came to know the working of the Francis turbine, right?
Yes, sir.
Okay. Shall I go for the next heading, that is Kaplan turbine in this? Just within few minutes, I'll complete the Kaplan turbine. So this Kaplan turbine, this is the major point for the Kaplan turbine. You should remember this. It is an axial flow, low head reaction turbine. It is an axial flow, low head reaction turbine. Coming for the Francis, it is mixed flow, medium head reaction turbine. Okay, like that you make a table by yourself. You prepare the table by yourself by picking up these points. Kaplan turbine, under the Kaplan turbine, right, this is axial flow, low head reaction turbine. Like that, you write down by yourself. It is similar to the Francis turbine, except the runner and the draft tube. I'll show you what is the meaning of how the runner will be. The runner, we are going to call it as a boss or a hub. The runner, we are going to call it as a boss or hub. Other name for the runner, I can call it as boss or hub. But that can be called only in the Kaplan turbine, not for the other turbines. Other turbines, we'll call it as a runner only. But here, just to differentiate the different turbines, we're going to call it as a boss or a hub, which resembles the propeller of the ship. Have you seen the propellers of the ship, no? At the front portion of the ship, there will be like a turbine. Have you seen? I'll play that. If you're not seen, I'll show that propeller of a turbine. What do you mean by the propellers of a turbine? Propellers of a ship. It will be same. The Kaplan turbine, if you see, it will be looking like the same as propeller of the ship. Hence, it is sometimes called as propeller turbine also. The other name for the Kaplan turbine is propeller turbine. Why? Because of the shape of the runner. The runner shape in the Kaplan turbine as well as the propeller of the ship will be similar. So it is called as propeller turbine. Here, how the water enters, the water flows parallel to the axis of the shaft. But how the water is flowing in reaction turbine? The water is flowing radial. Entry is radial, exit is axial. But here, both are axial. Entry is also axial, exit is also axial. How? I'll show you. This figures look like same as a reaction turbine, means same as a Francis turbine. If I show the 3D figure of that, it will be easy for you. Only difference you can identify here is that this is called as rotor blades. This is called as rotor blades or a boss or a hub. How many blades are there? Maximum in a Kaplan turbine, we can have only 4 or 6. The outer portion, everything is same. The water enters to the penstock. From the penstock, it will enter to the spiral casing, or it is also called as a scroll casing. From the scroll casing, the water enters to the guide blade. From the guide blade, it will enter to the rotor or a boss or a hub. So where for the Kaplan turbine, the number of blades will be only 4, maximum 6. If you go for the Francis, you can see the fixed picture. The water enters to the penstock, scroll casing, guide blade. Till here it is same. Only this portion is removed. This portion for the Francis turbine, the number of blades will be 12 to 16. Here, you observe this portion. But here what will happen? The number of blades will be only maximum 6. Usually in all the cases it will be 4. Maximum it can extend up to 6. That's all. Okay, that's what it is written here. Runner blades or runner vanes, scroll casing, L-shaped draft tube, guide vanes. These are all you can go through. Next. So what is how it is going to work? See, the Kaplan turbine is an axial flow reaction turbine. The water flows through the runner of the turbine in axial direction And the energy of the inlet of the turbine is sum of kinetic and pressure energy. See, as it is coming under the reaction turbine, the energy available at the inlet of the turbine is both addition of kinetic and pressure energy. That you already know. I told that before the class. Next, in an axial flow reaction turbine, the shaft is vertical. The lower end of the shaft is larger and is known as hub, the boss. Vanes are attached to it, or buckets are attached to it. Instead of buckets, we'll call it as a vanes. Next, if the vanes are adjusted, then it is known as a Kaplan turbine, and if the vanes are non-adjustable, then it is known as a propeller turbine. I hope this point helps you to differentiate the propeller and the Kaplan turbine, because if I see the center portion of the Kaplan turbine as well as the propeller turbine, I cannot differentiate. If the vanes are adjustable, then we are going to call it as a Kaplan turbine. If it is not adjustable, if it is welded and it is fixed permanently, then it is coming under propeller turbine. And this is about the draft tube. This is about the draft tube. Where what is the meaning of a draft tube? Can anyone tell? One or two? Generally, I'm telling. Don't read that. Just you tell what do you mean by the draft tube.
So where the water exits after getting propelled.
Yes. The draft tube is a conical tube where it is attached to the outlet of the turbine. And see, this is, for example, these are all called as a draft tube, different shapes of draft tubes. This is, we'll call it as one end, and this one we'll call as other end. See, in all the cases, smaller diameter will be, this smaller diameter, wherever it is there, this will be attached to the outlet of the turbine. And this bigger diameter or bigger size at the outlet will be dipped in the water. That I will show you once, or else if you go for the, if you have a lab in fluid mechanics, if you go for the experiment called reaction in Kaplan turbine, you can see this draft tube. A smaller diameter of the draft tube is attached to the exit of the turbine, and this bigger mouth or bigger diameter of the tube will be dipped in the water. Means the water level will be up to here. This will be dipped. Why it is done so? Because to provide the airtight casing for the scrolling, for the scroll casing. And remember, this draft tube is used only in the reaction hydraulic turbines. Only it is used in hydraulic reaction turbine, not in the impulse turbine. Okay? How? Why? Because in the impulse turbine, the water exits to the atmospheric pressure only. But here, everything, the entire casing, everything should be maintained with the different pressure compared to the atmospheric pressure. To maintain the difference between the atmosphere and inside the casing, this draft tube is attached or fixed. This is very, very important. Draft tube, so many times he has asked, with an 8 figure, explain the different types of draft tubes along with its function. You can see the previous question paper. In most of the question paper, this question will be mandatory. Along with the different figures of the draft tube, mention its advantages or what is the application of a draft tube. Like that, some other way he'll ask. We'll see here. Here we are having so many types of draft tubes. The figure E called as simple elbow type, B called as conical tube, C called as circular inlet, square outlet, and the D called as Moody's bell-mouthed tube. Moody's bell-mouthed tube. Where here, if you go for the simple elbow, it is a smaller in length, small length of the shaft. Means this will be used. This type of turbine will be used. This type of draft tubes will be used only in whenever the turbine shaft is small, less head is less head, and the percentage in this case of draft tube will be having only 60%. This conical draft tube is the angle of the cone is 8 degree, efficiency is 90%, lower specific speed turbine can be used in this. Then circular outlet, square output will be having efficiency of 80%, bell-mouthed will be having 80%, 85%. Then you can ask, sir, in this 90% efficiency is the bigger one, I can use the conical draft tube everywhere. This can be used everywhere because the efficiency is more. Yes, of course, it can be used, but there is some limitations regarding the head also. So see here, low specific speed turbine, I can use only this for low specific speed. If the specific speed is high, I cannot use this. Okay, and the height between the tail race and the turbine is higher, I cannot use this. Then I'll go for this type of draft tubes. So there are limitations to use each and every draft tubes they will use as per the availability of the size and then availability of the space in the plant. Okay, before going for the video of difference between the turbines, just I'll play you a video of Pelton turbine. Yeah, Pelton wheel turbine. Yes. Sure.
Reaction turbine. Now we shall see the working of reaction turbines. The reaction turbine, as the name suggests, works on the principle of reaction force, which is experienced by the turbine blades when water flows over them. The first set of blades are fixed and they convert part of
See, here he is explaining about the reaction turbine. Under that, Kaplan as well as Francis. See, for looking, it look like same. But what are the difference? He will mention. Observe that.
of water into kinetic energy. Water then moves through the moving or the runner blades. The moving blades have the shape of an aerofoil. When water flows over them, because of its shape, there is a reduction in pressure along its blade. Its velocity also changes along the blade. Hence, the water indirectly exerts a thrust force on the turbine blades. This force rotates the turbine blades. The rotation is thus partly due to an impulse on the moving blades due to the velocity of water and partly due to the change in pressure. As the water flows under a pressure over the moving blades, a closed casing is required in a reaction turbine. In an impulse turbine, the pressure along the blade is constant and atmospheric. It does not play a role in creating the force. So the casing in an impulse turbine is only to prevent splashing of water. The reaction turbine is used for medium head and discharge or low head and high discharge. Now, of the commonly used reaction turbines are the Francis turbine and the Kaplan turbine. Francis turbine. The main parts of the Francis turbine are a volute casing, guide vanes, runner plates, and a draft tube. From the casing, water passes through the guide vanes. Starter blades are arranged along the periphery to guide the water into the runner blades. Through the guide vanes, water enters radially into the rotor blades. The runner of the Francis turbine has a special construction as mentioned before. When the water enters radially, it starts rotating because of the pressure difference created by the aerofoil structure. During the process, the entire pressure energy of water is converted into kinetic energy. So, the water, after passing over the runner, possesses low pressure. The kinetic energy is also converted by the reduction in velocity when it flows over the blade. It is the net pressure difference from the inlet to the outlet which determines the energy from the turbine. To achieve a maximum difference, the outlet pressure is kept very low, sometimes less than the atmospheric. This will prevent the natural flow of water from the outlet. A draft tube corrects this. Water at the low pressure from the turbine flows through a tube called a draft tube. This has a gradually increasing cross section, so the pressure increases and the velocity decreases during the flow in the draft tube. At the end of the draft tube, pressure of water will be at nearly atmospheric pressure. So this eliminates possibility of water going up from the reservoir to the turbine. Since the water enters radially and leaves the turbine axially, Francis turbine is also called as mixed flow turbine. The lower Periyar project in Kerala uses a 3 Francis turbine of 20 megawatt, each at a rated head of 184 meters. Kaplan turbine. In Kaplan turbine, water enters through the casing and flows through the guide blades. Water enters into the runner blade portion axially. The runner blades are designed in a specific aerofoil structure like in the shape of the blade is a bit different. The blades are a bit lengthy and curved. Water hits the runner blade and exerts a thrust on it. This causes its rotation. The water, after imparting the energy, then flows axially out of the turbine and into the tube tube. This has the same function mentioned before. Kaplan turbines are usually used as a third stage turbine at low heads, typically below 40 meters. It is used to extract the last bit of energy from water. Besides this, it is also used in ships for its propulsion. The Kallara project in Kerala uses 2 Kaplan turbines of 7.5 megawatt, each at a headed rate of 45 meters.
Hello?
Yes, sir. Yes, sir.
So I given complete detail about the turbines regarding the plant Pelton, Francis and Kaplan. Instead of simply presenting the PPT, I have made use of the videos also. So that it will be better to understand how the turbines are going to work. Okay. Then in the next class, what I will do is I will show the difference between all the turbines. Just I will show one video which explains the difference between all the turbines and what are the key points to understand for each and every turbine. That I'll show, and then I'll wind up the theory of this module. Is that okay? After showing one more video in this, I'll wind up the theory part in the hydraulic turbine. Is it clear?
Yes.
Okay. So all of you type your USA number, be in class. Next faculty will join with this class. If you're having any doubts, you can discuss meanwhile. Okay. All of you type your USA number in the chat box. If anybody is having doubt, you can ask me. We'll discuss. I'll be in class. If anybody is having doubt, ask me. If no doubt, shall I leave the class? Okay, thank you. I'll leave the class. All of you attend the quiz and then upload the answers to the quiz. Thank you.
Thank you,
Okay,
sir.
I'll leave the class now.